Hi, welcome to my channel. This is Maker in Mayday. This video shows the process of how I recycled failed filament prints to make a soldering pen stand. A few days after buying a 3D printer, I couldn't stand the amount of waste it produced. It's not really about the money, I just believe we shouldn't waste too many resources while we're alive. Very few people are great enough to leave behind something that benefits future generations. If we're not contributing, then we're just consuming resources. Expanding the good and minimizing the harm, that's basically my life philosophy. Until I can afford a filament recycling machine, I'll probably try every possible way to use up the waste. For example, by melting it into easy-to-handle strips and, in this project, turning it into a soldering pen stand. The original idea was to make strips similar to the filament used in 3D printers. So I carved a piece of wood and melted the failed prints onto it, slowly forming them into a spool. It sounds a bit far-fetched trying to manually mimic what a machine produces. But that's just how I am. If I think of something, I'll give it a try. And then I come to the same conclusion: only a fool would do this, and that's when I stop. You can only see farther by standing on the shoulders of giants. But hearsay isn't a good enough reason to give up. Growth is. After melting it into straight strips, I found that they couldn't really be wound into a spool and would break into segments. Plus, due to the poor quality, some finished pieces would snap during use, so I still had to fuse them together with other plastic strips. In the end, I decided that making straight strips of an acceptable length was good enough. Eventually, I even realized I didn't need the carved groove as a mold. I could just melt the plastic directly onto a board and shape it into strips as I went. To be honest, even with the groove, the melted plastic lines came out looking like a pile of hay full of sharp edges and gaps. Next, like assembling a model kit, I glued the pieces on one by one. From assembling this simple frame to editing the footage and publishing the video, quite a bit of time passed, probably around 2 weeks. During that time, YouTube would occasionally recommend videos about filament or plastic recycling. These generally fell into two categories. One was plastic bottle recycling. /snapshot. I've listed the links in the video description. Come to think of it, most recent videos related to 3D printers tend to focus on introducing new machines. Maybe when 3D printers first entered the consumer market, a lot of people made compilation videos of interesting designs. When I first got my own 3D printer, I was also drawn to model sharing websites like Printable and Maker World. At that time, it felt to me like these model sharing websites provided everything I needed. Perhaps that's why it's now harder to find research-focused videos in 3D printing on YouTube. Whether that shift is good or bad is another question. But if fewer people are watching, there's naturally less motivation to make such content. This plastic bottle recycling experiment was actually published more than a year ago. There are also other similar videos, all of which have been around for over a year. Most makers probably have a habit of reusing materials. After all, not every experiment succeeds, but every one costs money. So saving where you can makes sense. At first, some may think that PET bottles are just another type of plastic and can be recycled into filament. But anyone who has done some 3D printing will likely have noticed that even among plastics, the quality can vary hugely. It's not just a matter of good or bad. For example, PLA usually needs a melting temperature of around 210 degrees Celsius, but that temperature isn't enough to properly fuse PET bottles. To be specific, if you stack 2 layers of PET bottle and try to weld them with a soldering iron set at 210 degrees Celsius, they'll soften but can still be easily pulled apart once cooled. On the other hand, solid PLA prints aren't that easy to break, based on my experience of melting waste into sticks. Perhaps inspired by these early recycling attempts, 3D printer manufacturers have developed more and more types of filament, some harder, some more resistant to warping, and others, like flexible materials, which I find especially interesting. Currently, the strongest flexible material is still liquid molded silicone, which also has high heat resistance. Back to the topic of videos about recycling PET bottles. After cutting the bottles into strips, they go through a melting process where the plastic strips must first be pulled through a heater. This actually shows that the recycling process just changes them from flat strips into round tubes. Melted PLA, on the other hand, can't hold its shape at all, let alone be pulled through a heater. For me, all my material comes from failed PLA prints, so this type of recycling process isn't applicable to me at all. The next method is a dedicated solution for filament recycling, but it involves spending money on equipment. This was actually the first method I came across, but I kept trying to avoid the cost. After melting a few batches of waste, I came to understand that the expense is unavoidable. Realistically, to make good filament, at the very least, filament that doesn't break mid-print, you need to apply pressure during the melting and remolding process. Let's compare this to a 3D printer's extruder. Like the PET recycling method mentioned earlier, a 3D printer's extruder pulls filament through a heater. The difference is that in the 3D printer, the filament is pushed into the heater before it melts, whereas in the recycling setup, the already deformed material is pulled through the heater. However, the waste material being recycled often varies in size, and forcing something into a high-temperature device is inherently dangerous. Safety equipment alone is already a significant expense. That's why, in mechanical engineering, there are specially designed systems for handling high-temperature and high-pressure operations. The extruder design shown here is one such example. In this process, instead of applying pressure directly at the material's entry point, a heated tube with a screw mechanism pushes the raw material toward the output. The width of the filament at the output is likely much larger than what comes out in a clean strand. So the commercially available filament that maintains a consistent 1.75 mm diameter is actually the result of very precise engineering. That's all for my learning and thoughts on filament recycling solutions. That's it for this video. See you next time.